on coherent spin dynamics, and it was carried out on 2 samples. The first one being cesium lead bromide, and the second one was the isotopically purified zinc selenide quantum wells. Okay, before that, now I'll try to answer those questions that were posed before. I'll do my best. So the first thing that we need to do for a spintronic device is that we need to generate the spin. Okay, so this is done by optical spin pumping is one of the techniques that can be used for that. So we pump these electrons from the valence band to the conduction band, and we spin pump them. Now, how do we do that? We go there step by step. First, if we consider the first figure on the left side here, this shows the basic band structure of a conventional semiconductor. The spin-orbit coupling can be represented as a vector addition of the orbital angular momentum L and the spin angular momentum S. So when this when the spin-orbit coupling effect takes place, what this does is it creates heavy hole states, the light hole states, and the split of states. You can see them in the band diagram as well. The split of band is the one which we are most interested in, and the energy difference between the heavy holes and light hole states, and this is called the split of energy. So this is represented as SO here. Now, the basic selection rule that we need to follow for the spin pumping to take place is that the Z projection of the total angular momentum should be equal to plus one or minus 1 between the 2 states, the final and the initial states between which the transition is about to take place. So this momentum of plus minus 1 can be provided by a circularly polarized light. The left circularly polarized light contains the projection equal to -1, and the magnitude is of course minus h cut. For the right circularly polarized light, it is plus h cut. Now, we'll just take the left circularly polarized light case for the time being, which has a minus h cut as the projection of the total angular momentum. And we take the excitation energy to be equal to Eg. This means that only transitions that can take place for the moment are between the valence band and the conduction band. There's only, and the solid lines, you can see these solid lines, they represent the allowed transitions for the left circularly polarized photon right now. So we can see that the transitions that can take place for the left circularly polarized light is from the heavy hole state plus 3/2 to the spin state plus half in the conduction band, and from the light hole state, a state of plus half to the minus half spin state in the conduction band. Now, the heavy hole transitions have a greater probability of taking place 3 times more than that of the light hole. So this gives us a degree of polarization of about theoretically about 50%. This is how this is a degree of spin polarization. Now, if we add the split of states into this equation as well, if we increase the excitation energy, that is, and excitation energy now, if it is equal to Eg plus delta SO. So now the split of states will also play their part in the spin pumping. Now you can see that the state for the left circular polarized, the transition that is possible is from the plus half split of state to the minus half state of the conduction band. So this actually is pumping the electrons in the other spin state, in which opposite to the state in which most of the spin polarization was present before. So this has an effect of a reduction of the spin polarization in this material. Now, if let's say the split of energy is much greater than compared to the band gap, or it has a good magnitude, the splitting of the mixing of these states, the split of states with the valence band states, will be reduced down to a minimum. So this will help to increase the degree of spin polarization. The total electron spin can then be calculated by multiplying by the vector addition of the multiplication of the probability and the spin magnitude. And in order for the conservation of angular momentum to hold, this hold would also have a spin on it, and the total angular momentum would be equal to plus minus 1 based on which photon you are looking at. Okay, now we move on to a quantum well structure. What happens in a quantum well structure? In a quantum well structure, the light hole states and the heavy hole states, they are split due to the quantum confinement effect, so they get split up. So now the only transition now that can take place for, let's say, a left circularly polarized light is from the heavy hole state of plus 3/2 to plus half state. There is no spin pumping into the other state. So all the polarization that there is is in this one state. So this gives you 100% degree of spin polarization, which is quite favorable for spintronic devices. Okay. Now the really interesting part and the really interesting thing about perovskite structures, we discussed this in the first section in the computational study, that we have an inverted band structure for a CSP-BBR3. Now, if you consider this inverted band structure in figure 2, now if we excite this material at its band gap energy, the only spin polarization, the only transition that is allowed at the band gap energy is from the plus half state in the valence band to the minus half state in the conduction band. So this gives 100% degree of polarization in its bulk state, which is very interesting, which makes these materials so exciting for spintronic devices. This was the main part of this. Okay, now we come to how we control and manipulate the spin. So now we discussed optical spin pumping. All the electrons can be spin pumped into one direction, and we have a certain degree of spin polarization of that. Now, inside a material, due to the spin orbit coupling effect, whereas a high spin orbit coupling effect is useful to achieve higher degree of spin polarization, but when it comes to the spin relaxation of the carriers, especially the electrons, they play a detrimental role. Because what happens that when due to the spin orbit coupling effect, there is an effective magnetic field present within the sample or within the material under consideration. And this effective magnetic field is fluctuating in nature. So this fluctuating magnetic field or fluctuations, it causes the electron spins to depolarize and to dephase. So what we do in order to overcome this, we apply an external magnetic field, which is stronger than the effective internal magnetic field. We apply this field. What this does is there's two things, or you can interpret them as in two different things. It causes Zeeman splitting, of course. We're applying a magnetic field. It will split the magnetic states up in the spin half, this here, spin half and spin up and spin down states. Okay, and as the electrons are spin pumped into the conduction band, then it creates a superposition of these two states. Due to the Zeeman splitting, it creates a superposition of states. The magnetic field now can be applied in a direction that is perpendicular to the spin polarization. This is called the Fourier geometry, or it can be applied in the direction of the Z projection of the spin polarization. This is called the Faraday geometry. The time it takes for the electrons to decohere or dephase in a Fourier geometry is called the spin dephasing time. It occurs because of the random scattering events that can take place, and also because of the G-factor spread in the ensemble of the electrons that are present within the material. Whereas the time it takes for the spin to decay down in Faraday geometry is called the longitudinal time, and it's represented as T1. The spin dephasing time is represented as T2 conjugate. So Larmor precession, yes, I forgot it. This shows, this dotted line shows the Larmor precession that takes place due to the magnetic field. Zeeman splitting Zeeman splitting is considered to be the quantum mechanical case of Larmor precession. They're considered to be the quantum mechanical and the classical analogs of each other. So in terms, if you can think about it in terms of in quantum mechanical terms, the Larmor precession represents a time evolution of the coherent superposition of these two Zeeman split states. Okay, so this was the basic optical setup that was used to characterize and to study the coherent spin dynamics within these two samples. The first thing we need to know is that it is a pump probe setup. In a pump probe setup, what it does is it has two beams of light. The pump beam, which is a stronger beam, it basically creates an effect within a sample. When it creates the effect, the probe beam goes into the sample and it detects the change that was created by the pump beam. So this is the basic concept of pump probe setup. So I'll first introduce some of the major components that are involved in this setup, and then I'll follow the light path and explain what's going on in the setup and how we use this setup to achieve our results. One of the main most important components is the titanium sapphire laser. The titanium sapphire laser had a frequency, has a pulse frequency of about 76 megahertz. This corresponds to a time of 13.2 nanoseconds between consecutive pulses. Okay, this laser can be tuned within the wavelength range of 650 to 1100 nanometers.
You have to mention that this is a oscillator, isn't it? A TISF laser.
The
Can you hear
oscillator
me?
is in. Yes, sir, I can hear it. The oscillator is in there. Yes.
Yeah. Okay.
Okay. So so thanks, sir. So this is the wavelength range that it can operate in. It's about 650 nanometers to 1100 nanometers. So the samples that we had, they required higher energies and lower wavelength, the resonance energies, and we needed to excite the samples at the resonance energies. So we did not, the titanium sapphire laser did not provide enough energy of the photons for it to excite our samples at resonance energies. So we used an optical parametric oscillator to increase that. What an optical parametric oscillator does is that it uses a titanium borate crystal, and it makes use of the second harmonic generation to double the frequency that is input into it. So this is the OPO function. Both these beams were modulated. The probe beam was modulated by a photoelastic modulator, whereas the pump beam was modulated using an acousto-optic modulator. And now we come to the cryostat. The cryostat.
The OPO, actually, you are saying you are using the BBO crystal, isn't it?
TBO, titanium borate.
Okay, for doubling.
Yes, sir.
For doubling purposes.
Yes, sir. Yes, sir. Frequency doubling. Yes.
Okay.
Okay, so this is the magneto-optic cryostat. This cryostat could provide temperatures down to the cryogenic temperatures of about 2 kelvins. And the magnetic field, the highest magnetic field that it could provide was about 10 Tesla in each direction, Fourier geometry and Faraday geometry. So, so this was, and the sample was placed within the cryostat, and the magnetic fields were applied. The delay line is also one of the most important components of this. We needed a time resolved spectra. This delay line is responsible for generating these kinds of spectra that you see here for the Fourier geometry and for the Faraday geometry. This kind of time resolved spectra are obtained using this optical delay line. What an optical delay line does is that it creates a time difference, a time delay between the pump and the probe pulses. We need that time because the pump pulse will go into the sample and will create an effect. Then we need a probe beam at a delay and at a time later than the probe beam in order to see what happened inside that. And so the delay is adjusted using a motorized stage. The delay is increased and decreased at different increments in order to get this kind of a spectra that we see over here on the right side of the slide. Okay, the Wollaston prism is at the detection stage. What it does is that it divides the incident light that's coming into it into two orthogonally polarized components, and it creates an angle between them. It transmits them at different angles, and this was then input into a balanced photoreceiver. A balanced photoreceiver basically takes the difference of these two signals that are provided, and it amplifies it. And the lock-in amplifier then demodulates the probe beam signal, and that can be seen in a lab view application. The data can be acquired by a lab view application in a PC. Okay, now let's follow the line of the laser. The first thing that if you look at it after the OPO, the optical beam splitter splits the beams in. Yes,
can you please explain a bit what does AOM actually doing here?
The AOM is a piece. It modulates the light. It's a piezoelectric device that creates a sound wave. Okay, it generates a sound wave and a grating of a sound wave. So when the light interacts with this sound wave grating, it causes diffraction. Okay, it has a formula of 2 lambda equals to 2 sine theta n lambda kind of thing. It's the diffraction. I don't have that exactly in mind, but what that does, it allows the modulation of the intensity of the probe beam of the pump beam here. Yes.
Okay.
Okay, so if you follow the path, now the pump beam has been pump beam and the probe beam has been divided. So the delay line causes the delay in the pump beam, and then the lambda by 4 plate, which is a quarter wave plate. What it does is that it converts the linearly polarized light, which is the pump beam till here, and it converts it into circularly polarized light, because that is what we need for the spin polarization to take place, spin pumping to take place, which was mentioned in the previous slides. Where the probe beam remains a linearly polarized light. A linearly polarized light is basically a superposition of the left circularly polarized light and the right circularly polarized light. Now, how is the linearly polarized light going to detect the spin polarization within this sample? In a spin polarized sample, let's say whichever direction the spin polarization is in, these two components will have different absorptions based on the kind of spin polarization and the direction of spin polarization within the sample. So they will have different absorption rates within such a sample, such a spin polarized sample. So as a result of that, the refractive indices of these two components, these two left circularly polarized light and the right circularly polarized light that compose the linearly polarized light, they will experience different refractive indices. As a result of this difference in the refractive index of these two components, we see a rotation of the polarization. You can see in down here, which I'm pointing with my cursor. This is called the magneto-optic Kerr effect. So if we can measure somehow, find a way to measure this rotation, then we can also have a measure of how much the spin polarization is present within that, because this is proportional to that. This effect is proportional to that. How do we measure this rotation? We can do that. You can see that for a rotation, the vertical component of the polarization and the horizontal component of the polarization will also change. So this is what is achieved by the Wollaston prism. But what the Wollaston prism actually does is that it divides the light between these two vertical and horizontal components. And of course, these will have different intensities based on the rotation. So the light that we're coming out, the signal that is coming out of the Wollaston prism is actually a measure of how much the light has been rotated. The light polarization has been rotated. And that is what is actually being measured on the lab view application. And this represents the amount of spin polarization that is present. The only drawback of this setup is that it cannot measure spin lifetime, which are greater than 13.2 nanoseconds, because that is the gap between the two pulses. So what a greater lifetime than this value would mean that even before the system has decayed completely, the spin lifetime is decayed completely, the other pulse comes in again and spin polarizes the system again. So there is no way that we can calculate a spin lifetime from this kind of a setup, which is greater than the time between the two pulses, two consecutive pulses, which is 13.2 nanoseconds. Okay, this was the